going to continue on with the notes, chapter 11 notes on molecular geometry. What we did already was talk about molecular geometry of molecules where the center atom has no lone pairs. So if there's two atoms attached and something has no lone pairs, the molecule is linear. An example analogy I gave with that is you're walking with two of your friends. They're not friendly to each other. Well, the thing is they repel each other. And so you're in the middle and your two friends on either side. It's linear. If you're walking down the street with three of your friends and none of them or they all repel each other, again, it's valence shell electron pair repulsion, VSEPR theory. So it's just an analogy when I say your three friends don't like each other. What shape would you walk down the street is you'd be in the middle, one in, you can say front or behind, one towards the left, one towards the right, okay, and towards the front. So the shape would be trigonoplanar. Four atoms attached lone pairs, the shape where the maximum distance where they're furthest away from each other is called tetrahedral. The angle is 109.5 degrees. You don't really need to know that angle, but that's what it is. Okay, and so the idea of all this is when you have shared electrons, they repel each other. Valence shell electron pair repulsion theory. Well, it's not just shared electrons that repel each other, also unshared electrons repel each other. Unshared electrons, when you have lone pairs of electrons, also repel each other. So if you had CH4, that's four atoms attached, no lone pairs. The shape of them, four atoms attached, lone pairs. The shape is called tetrahedral. But what if you had a molecule where you, like NH3, nitrogen, ammonia, NH3, where there is a lone pair. If you drew the Lewis-Dot structure NH3, nitrogen's the center, you would have three hydrogens attached and a lone pair. This lone pair of electrons also repel the shared pair of electrons. So the overall shape looks like tetrahedral, but this unshared pair of electrons actually repels these other electrons, making the angle just a little. These lone pairs of electrons pushes these shared electrons a little bit more, such that the angle is a little bit less than 109.5. In this case, 107.3. Though it's not much difference, but it is technically a little bit less. If you had two lone pairs and two bonded atoms, so a total of four things, two bonded atoms, two lone pairs. So that's four things total. Well, if it's four things attached, no lone pairs, it would be tetrahedral, but two of them are lone pairs. What shape is left is something called bent. And we're going to get to the name of that in a few minutes, or actually in the name of this one as well. But notice the angle actually decreases a little bit more. These lone pairs of electrons bends these case hydrogens a little bit more, such that each time it gets smaller and smaller and smaller. Okay, so that is some of the differences when we have lone pairs. So the rest of the notes today are going to be about once I have stuff with lone pairs. So again, once I have lone pairs, the lone pair versus lone pair repulsion is greater than that of lone pair versus bonding pair repulsion. Meaning this lone pair right there is going to be greater than between these bonding pairs, making the angle a little bit less and a little bit less each time. You don't really need to know the angles of it. It's just that these lone pairs push the bonding pairs in a little bit closer together is the point, overall idea. Okay, so notice again 109.5, 107.3, 104.5. You don't need to know the angles, just that it gets a little bit less the more lone pairs you have. Okay, so when we say we have three bonded atoms and no lone pairs, the shape is trigonoplanar. Kind of looks like a Mercedes symbol. But let's say you had three things attached, but one of them was not an atom, but you had a lone pair instead. So you had two bonded atoms to the center and one lone pair. The shape of that molecule, normally it would be trigonoplanar, but one of them is a lone pair. So what do you have left is a shape that looks like this. It's bent. It's bent. Sulfur dioxide, I believe, is a Lewis-Dot structure, something like this. Sulfur surrounded by two oxygens, and there's a lone pair, I believe, on sulfur dioxide. That molecule is bent shape. So what if I had normally four bond atoms, no lone pairs? That shape is tetrahedral. But let's just say one of them was actually a lone pair. So you had 4 things attached. Well, but one of them is a lone pair. 3 plus 1 is 4. 4 things attached to the center, and one of them was a lone pair of electrons. The shape of that thing is trigonopyramidal. Normally, 4 things attached, 1 lone pair, it's tetrahedral, but if one of them is a lone pair, the shape is pyramidal. Let me go back a second, because there was an example right here. NH3, ammonia. If you drew the Lewis dot structures, there's 3 bonded atoms and 1 lone pair. That shape here is trigonopyramidal. So the shape of 3 bonded atoms, 1 lone pair, the shape is trigonopyramidal. If you had 2 bonded atoms and 2 lone pairs, normally 2 and 2 is tetrahedral, but if 2 of those things were lone pairs, the shape that you have left is also known as bent. The water molecule, Lewis dot structure water, has 2 bonded atoms, 2 hydrogens, and 2 lone pairs on the center atom. Remember, this is all based on the center atom, based on the center atom. On the center atom, oxygen, I have 2 atoms attached, 2 lone pairs. This molecule is bent. So 5 atoms, no lone pairs, the shape is called trigonobipyramidal. But if I had 1 lone pair on it, 4 bonded atoms and 1 lone pair. So 4 bonds, 1 lone, okay, 5 things total normally is trigonobipyramidal, but if one of them's a lone pair, then what you have left is this shape, where you have an A there, a B in the front, B in the side, 1 on top, 1 on the bottom. That looks kind of like a weird, well, it looks like that. Okay, I will not even describe that. There's a name for it, and actually there's 2 names. One is called a distorted tetrahedron. It looks like this. It's also known in the book as seesaw shape. And you can kind of see as a seesaw, if you look at it towards, like, if this is the base and this is the seesaw, then it can go back and forth on either side. This is also known as a seesaw or distorted tetrahedron, the same thing. So if you had 4 bonded atoms, 1 lone pair, the shape is called a distorted tetrahedron or seesaw. If you had 3 bonded atoms, 2 lone pairs, so a total of 5, 3 plus 2 is 5. Normally it's trigonobipyramidal, but you have 2 lone pairs on it. What shape you have left is A in the center, B on top, B on bottom, 1 sticking out. That looks like a T shape. In fact, that's the name of it. It's called T-shaped. So 3 bonded atoms, 2 lone pairs on the center atom. The shape is called T-shaped. If you had 2 bonded atoms and 3 lone pairs, 2 bonded atoms and 3 lone pairs, what you have is A is the center. You have 1 atom top, 1 atom bottom, making a straight line, or in other words, linear. So I3, if you had that I3, the Lewis dot structure, the center iodine has 3 lone pairs on the center and attached to 2 other atoms. Two atoms attached, 3 lone pairs. The shape is called linear. Everything on this slide right here, though, notice 5 things attached, 4 and 1, 3 and 2, 2 and 3, 5 and 0. These things are all exceptions to the octet rule. Because octet rule, you should only have like 4 things. These are exceptions to the octet rule. So that, well, it's an exception to octet rule. 6 things attached, no lone pairs, the normal shape is octahedral. But what if one of them was a lone pair? So you had 5 atoms attached and 1 lone pair. 5 and 1, which is 6. The shape of that thing, again, normally is octahedral, but one of these atoms is actually a lone pair. Then what shape do you have left? The shape that you have left is right here. And notice the shape is called a square pyramidal. Notice you have a base is a square. And on top, well, another atom, such that the shape here is called square pyramidal. It looks kind of like the squares and the pyramids in Egypt, where you have a square base pyramid, unlike the trigonopyramidal, which is a triangle base pyramid. This is a square pyramidal shape. If you had 4 bonded atoms and 2 lone pairs, 4 bonded atoms and 2 lone pairs, the electrons are 1 on the top, 1 on the bottom. What you have left is a atom here, one there, there, and there, you have a square planar. In fact, that's the name. Square planar. So the shape of the molecule is called square planar, where you have an atom, center atom, surrounded by 4 atoms all around it, all in one plane, and it makes a square planar. Okay, so that's a lot of shapes, but there's a kind of a summary on here. Table 11.2, that should say 11, okay? Table 11.2 in the book tells you the different shapes. If we're only going to look at the second and third, well, this is third and fourth column here. Number of bonding pairs, number of lone pairs, based on the center atom. If you had 2 atoms attached, 1 lone pair, the shape is called bent. 3 bonded atoms, 1 lone pair, the shape is called trigonal pyramidal. 2 bonded atoms, 2 lone pairs, the shape is called bent. 4 bonded atoms, 1 lone pair, the shape is called distorted tetrahedron or seesaw. 3 bonded atoms, 2 lone pairs, the shape is called T-shape. 2 bonded atoms, 3 lone pairs, the shape is called linear. 5 bonded atoms, 1 lone pair, the shape is called square pyramidal. 4 bonded atoms, 2 lone pairs, the shape is called square planar. We use this to determine the shape of a molecule. So let's look at the overall rules to determine the shape of a molecule. Predicting molecular geometry, and it's going to be the last slide for today. First thing is you have to have the correct Lewis dot structure. I'm going to emphasize this, you have to have the correct Lewis dot structure. If you have the Lewis dot structure wrong, you will get the wrong shape or molecular geometry. So you need to have the correct Lewis dot structure. Once you have the Lewis dot structure, look at only the center atom. Count the number of lone pairs on that center atom, and the number of atoms bonded to that center atom. And the number of atoms, I don't care if it's single bonded, double bonded, triple bonded. Count the number of atoms attached to that center atom. That's all we care about. How many atoms attached to that center atom? Once you do that, it says use VSEPR to predict the geometry of the molecule. Meaning, for right now, look at this table. Okay, 3 atoms, 1 lone pair, trigonal bipyramidal. 3 atoms, 2 lone pairs is T-shaped. So I'm going to use that table to do this. If this was normal in-person class, I'm going to tell you on the test for this, you would actually have to have that all memorized. In case you're complaining like, oh, that's a lot of shapes to memorize. I believe I counted there's around 16-ish different shapes. You will survive memorizing 16 different things. Okay, I know you don't know it right now, and it sounds like, oh my goodness, that sounds like a lot of different shapes. You'll survive. It's actually not that bad. It's not that hard, okay, to memorize. Ooh, 16 shapes. Okay, you've memorized a lot more. Say a multiplication table is a lot more than that, and you did that in probably 3rd grade. Okay, so I'm going to do this as examples, 2 examples. What is the molecular geometry of sulfur dioxide and sulfur tetrafluoride? SO2, SF2. Let's start with sulfur dioxide. First thing, draw the Lewis dot structure. I'm assuming you know how to draw a Lewis dot structure. Here it is. This is a Lewis dot structure of sulfur dioxide. Okay, so step 1, draw the Lewis structure. Got it, there. I'm just telling you this in case you don't know. Next, count the number of lone pairs on the center atom and the number of atoms bonded to the center atom. How many lone pairs are in the center atom? Lone pairs, not single. How many pairs? You see the pairs of atom? How many pairs? A couple is a pair. There is 1 lone pair. Not 2 lone pairs, that's 1 pair of atoms. How many atoms are attached to the center atom? There are 2 atoms. It does not matter if it's double bond or single bond. There are 2 atoms, number of atoms bonded to the center atom. There are 2 atoms attached, lone pairs. Sometimes people write it as A, B, 2, E, but whatever. Just know there's 2 bonded atoms and 1 lone pair. So I'm going to look on the table before, on that last slide. 2 bonded atoms and 1 lone pair. Oh, it's the first one on here. 2 bonded atoms and 1 lone pair. I'm looking for 2 bond atoms and 1 lone pair. I just said is the first one. The shape of that molecule is bent, and look at that. The example is SO2. So the shape of that molecule is bent. I know that because there's 2 bonded atoms and 1 lone pair. Let's look at the next example. Sulfur tetrafluoride. Draw the Lewis dot structure. I'm assuming you know how to draw it. And here it is. There's a Lewis-Dot structure. Notice sulfur is the center atom. Count the number of lone pairs on the center atom. I see there is one pair. I know there's two atoms. A pair is two. There's one pair, one lone pair. How many atoms attached are bonded to the center atom? Count 1, 2, 3, 4. There are 4 fluorines. There are 4 atoms attached, one lone pair. 4 atoms attached to sulfur, one lone pair. 4 atoms attached to sulfur, one lone pair. 4 atoms attached to the sulfur, one lone pair. Let's look at the table for 4 atoms attached, one lone pair. I'm looking for the column where there's 4 and 1. It's not the first one. This is 2 and 1. Find 4 and 1. That says 3 and 1, 2 and 2. Right here, 4 and 1, assuming you can see it on your screen, okay? 4 and 1. The shape of that molecule is called distorted tetrahedron or sea salt, the same name, okay? Distorted tetrahedron or sea salt. So that molecule is called distorted tetrahedron or sea salt. So that's how we can predict the shape of the molecule. 1, draw the Lewis-Dot structure. 2, count the number of atoms attached and how many lone pairs. Then you can look at this table here to see how many atoms attached, how many lone pairs. And I'll tell you the shape of the molecule. This diagram or this table is if there's one or more lone pairs. What if there's no lone pairs? You have to go to table 1. Let me go all the way back. Table 1, just pass it. If there are no lone pairs, 2 atoms attached, no lone pairs, linear. 3 atoms attached, no lone pairs, trigonoplanar, and so forth. So this table, if there's no lone pairs, the other table, table 2, if there are lone pairs. And that's how we predict molecular geometry. Draw the Lewis-Dot structure, see how many atoms attached, how many lone pairs, and for now, look up either under table 1 or table 2 to determine the shape of the molecule. And yeah, that's it.